It's called Measurements Inside Black Holes. As with any title, it was designed to invite people to come to the talk. So it's great to be here. It's always fun to come to the KITP. It's exciting and daunting to be on the home turf of the AMPS team. So AMPS performed a great service by deepening our puzzlement about black holes and information, and also opening the door to audacious speculation. So I will be barging through that door today. And the talk is about trying to make sense of infalling observers who make measurements inside black holes, and also horizon straddling measurements made by observers who interact with both the outside and the inside. But I will do so in the particular context of post-selected quantum mechanics, a suggestion for thinking about black holes that goes back over 10 years to a proposal by Horowitz-Maldacena. And I talked about that subject at the KITP before, last August, but I want to go a little bit more deeply in this talk into the issue of how to make sense of the measurement theory, though I will, in the first half of the talk, explain the background of what that proposal is and why it is natural, from my point of view, to revive or think about that proposal in the wake of the AMPS puzzle. So post-selection, I'll explain what it is in a minute, but it has some virtues in the setting of black hole physics, which is why I think it's a worthwhile subject to think about. So one is, it provides us with at least a schematic understanding of how to reconcile semi-classical causal structure of a black hole with unitarity. Because there's a very hard to understand thing about black holes, which is they have an interior geometry, things can fall in, this stuff goes to the singularity insofar as we take the semi-classical causal structure seriously. What's supposed to happen to that stuff? How does it get out from there? And this proposal of Horowitz and Maldacena was an attempt in kind of a schematic way to answer that question. And there's a second virtue, which is that we can relax some of the constraints on the entanglement structure of the Hawking radiation that AMPS pointed out in this scenario, and maybe find ways around the puzzle. So those are the blessings that accrue, but there are also costs. And in particular, the whole reason to have this discussion, what motivates the proposal, is to make sense of quantum mechanics outside black holes. We're trying to save quantum mechanics. But to save it, we kill it, because we change the rules of quantum mechanics on the black hole interior. So it's questionable how great a triumph this is. Maybe it's not as bad as it sounds. Maybe this picture that I'm going to be describing can be reconciled with having the kind of local unitary description on the boundary of the space-time that we all expect and hope to apply. But when we try to extract the description of the emergent space-time described by that boundary theory, we should be prepared for surprises. That's part of what the AMPS puzzle is about. So this is a possible big surprise that could be lurking inside black holes. So what I want to emphasize today is that a picture like this leads in kind of a natural way to some non-local phenomena that can occur outside the black hole horizon in the bulk space-time, and we'd like to get an understanding of what those phenomena are and whether they're reasonable. But before I do that, I have to explain again the setting. So first of all, I should explain what teleportation is, because that's the basis of everything I'm going to talk about. So quantum teleportation is an example of how quantum entanglement can be used as a resource entanglement can be exploited to do things that we wouldn't otherwise be able to do without entanglement. So, for example, it may be that I intended to bring the quantum state with me from Pasadena to Santa Barbara when I was driving up last night, but I left it behind. And now I need this quantum state here today, but I don't even know what this quantum state is, so I can't prepare it from scratch here in Santa Barbara. I left it in Pasadena, but I come here a lot. So the last time I drove up from Pasadena to Santa Barbara, I brought with me half of an entangled state, which I had prepared at Caltech, and I left it behind. So it's right here in the building. Okay? And now I have this resource, which was prepared in my last trip, shared between Pasadena and Santa Barbara, and now I can use it today to teleport the state I left behind, even though I have no quantum communication available right now between Pasadena and Caltech. Classical communication, yet. I have a friend who's going to help me in Pasadena, can make a phone call, make measurements in Pasadena, and because of the entanglement resource, we had the foresight to prepare in advance. I can get my quantum state. So a maximally entangled state can always be written, can you see okay on top of the stuff? In some suitable basis as a sum of basis state, orthonormal basis state for the first system, tensored with orthonormal basis state for the second system. And actually, if I fix the basis, any maximally entangled state can be obtained from the standard one by applying a unitary transformation just to half of the state. So an arbitrary maximally entangled state can be written, say, as a unitary acting on the second system times the state I call phi. And it doesn't really matter which half of the state I act on. V acting on the right side is the same thing as its transpose acting on the left side. So I can write an arbitrary entangled state like that. And in the scenario I just described with time running upward, the preparation of an entangled state occurred a long time ago. And that state I can say some maximally entangled state, so I can certainly write it as I tensor V times my standard maximally entangled state. And some of that entangled state is here in Santa Barbara, but the other half of it is back in Pasadena. And there is a state that I left behind in Pasadena. And what my friend can do for me today is perform an entangled measurement, an orthogonal measurement onto a basis. All elements of the basis are maximally entangled. And so a particular outcome I can write as a projection onto some unitary tensor identity. And this really describes a mapping from this initial state to this final state, in which first the unitary U is applied and then the unitary V is applied. And so if my friend performs the measurement and gets this outcome, then if we post-select on that particular measurement outcome, then in fact there's a factor of 1 over d if I do this calculation because of the 1 over square root of d's in the expression for the state. But given that particular outcome, there's a unitary that relates the state which I left behind in Pasadena to the state we have now in Santa Barbara. Now, I happen to know, because I prepared it myself, what this maximally entangled state was, which we had prepared in advance. So I know V, but I don't know U. That was a measurement that my friend in Pasadena performed today and got a particular outcome, some particular maximally entangled state. So that's why she calls me up on the phone and tells me what that outcome was. And so now both U and V are known, and so I can apply V inverse and then U inverse and get a perfect copy of the state I left behind. But we never could have done that without the entanglement. I didn't know what the state was. My friend doesn't know either. She could have measured it, but her measurement would have damaged the state. And even if she told me information about the outcomes of her measurements, I wouldn't have been able to reconstruct the state here in Santa Barbara from that measurement data. That's quantum teleportation. It's an example of how entanglement can be a useful resource. This 1 over d means that the measurement outcome, any particular outcome of this entangled measurement, occurs with a probability which is 1 over d squared. There are d squared possible maximally entangled states that are mutually orthogonal. Each one of them occurs equiprobably with a probability which is the square of this amplitude. And I have to know what particular outcome was obtained in order to reconstruct the state. It's kind of irresistible to describe what's going on in terms of a flow of information through the space-time in which the initial state is propagated forward in time up until this Bell measurement was performed, then backward in time to the initial preparation of the entangled resource shared between Pasadena and Santa Barbara, and then forward in time to the state I'm holding in my hand now. And this description is just one in which we straightened out that time ordering. So it looks like first U was applied and then B.
Can you clarify what you mean by measurement? It sounds like your friend was simply applying this operator.
So what my friend, I'm sorry, I wasn't clear. What my friend actually did was an orthogonal measurement onto a complete basis of which there were d squared elements. Each element of that basis was maximally entangled.
Let's say it's a qubit. Your friend has a Stern-Gerlach apparatus.
Yeah.
What actually does your friend do?
Well, what my friend, so the question is, how do we do Bell measurement?
Yeah.
So let me, actually this is good because I'm going to need this later. So let me explain it in the case of entangled qubits, where there are 4 possible outcomes, and there's nothing conceptually different about higher dimensional systems. So suppose they're qubits. An example of a maximally entangled basis, forgive me for not writing the square root of 2's just to save myself the trouble, is 0, 1, 0, 0 plus or minus 1, 1, and 0, 1 plus or minus 1, 0. And I'd like to do a measurement in which each one of the outcomes corresponds to a projection in this basis. I can describe the elements of the basis this way. They are simultaneous eigenstates of 2 commuting observables. So what I'm really going to do is measure those 2 commuting observables. I can think of one of those observables as, I'll write it as a tensor product of 2 z's. Z is just the Pauli operator sigma z, but I'm avoiding writing the sigmas by just calling it z. And what z tensor z does is it detects the parity of these 2 basis states, whether their sum is odd or even. So these states are the ones with z tensor z equal to plus 1, and these have z tensor z equal to minus 1. Here parity is odd, and here parity is even. And the other observable I can write as x tensor x. So it's 2 Pauli operator sigma x, which flip 0 and 1. And this plus or minus I can think of as the eigenvalue of the operator x tensor x. Because if I do 2 flips, that interchanges 0, 0, and 1, 1, and depending on whether the space is plus or minus, the eigenvalue will be plus or minus 1, and likewise here. So I need 2 bits of information to pick out one of these orthogonal states, and I'm going to obtain it by measuring these 2 observables. Though z and x anti-commute, the tensor product of 2 z's commutes with the tensor product of 2 x's, so they can be simultaneously measured. So how am I going to do it? Well, my friend has a quantum computer, and she can perform 2-qubit entangling quantum gates. In particular, one useful for this measurement procedure is a controlled NOT gate, where if I denote the basis states by A and B, which can take the values 0 or 1, what the gate does, acting on that basis, is it flips the value of B if A is 1 and does nothing otherwise. So it just adds mod 2 and puts that in the second register and leaves the first qubit alone if it acts on that standard basis. So that's the C-naught gate. I'm using this to denote a C-naught gate. And now if I want to do the Bell measurement, here's some entangled state, and I don't know yet which one it is, or I want to project it onto this entangled basis. It might not have been entangled to start with. And I'm going to use 2 extra qubits as meters for my measurement. I'll call them ancilla qubits. I don't know, quantum information, people like the word ancilla, but it's a meter, a probe. I'm using all those words interchangeably. And so I can prepare one of these guys in the standard basis state 0. That's one of my ancilla qubits. And then I can perform 2 of these C-naught gates where I will either flip or not flip the ancilla qubit depending on whether this control qubit is 1 or not.
I'm confused as to which one is in Pasadena and which one is in San Diego.
Well, these are now both in Pasadena. This you asked what my friend does.
Yeah.
Right? I'm telling you what my friend did in Pasadena. And so, okay, you're probably bothered by this. Okay. They're just 2 qubits. They're 2 qubits, and I'm going to measure them.
I'm just not sure which qubit is where and who has access.
Okay. My friend, her name is Alice. My friend Alice has 2 qubits at home in Pasadena. Okay? And she wants to do Bell measurement on the 2 qubits. And I'm describing to you how she does it, making use of these coherent operations, the 2-qubit entangling gates, C-naught gates. And so she first does this, and then she measures this qubit in the Z basis. That means she projects onto the basis 0 and 1. What these C-naughts do is they will flip this bit in the standard basis either an even or an odd number of times, depending on whether the observable Z tensor Z is plus or minus 1. So when Alice performs a single, you'll let her do a single qubit measurement, okay? She can use your Stern-Gerlach apparatus for that. And so she then projects onto 0 and 1, spin up and spin down. And by doing so, she reads out the value of Z tensor Z and collects no other information. Okay? And then, but we're not done yet because we also have to measure X tensor X. So she prepares a qubit in the state that I'm calling plus, which is just the uniform superposition of a 0 and a 1. And now again, she'll prepare 2 C-naught gates, but she'll do it this way. And now, in the case where this is a 0, the C-naught gates don't do anything. In the case where it's a 1, they apply X to each one of the 2 qubits. So they apply X tensor X. And if X tensor X is equal to plus 1, nothing happens to this state. If it's equal to minus 1, the relative phase of a 0 and 1 flips. And so she can read out in the X basis, that is, project onto the basis 0 plus or minus 1, and read out the value of X tensor X. Okay? So that is a procedure for performing the entangled measurement. There was a question.
Yeah. What happens if you have a phase between 0, 0, and 1? General.
What if you want to project onto a different basis?
Well, no, I was going on the lines that atom quantum teleportation is really supposed to even contain all the phase information, so not just those 43 choices, but really the full state with all the phases and everything.
That's right, but that part works, right? Because what you're saying is, what if this state is some arbitrary coherent superposition of the basis state? So in the case of the qubits, it could be some superposition of 0 and 1 where A and B are complex numbers. But the procedure that I described here, in which we prepare the maximally entangled state and then project onto the maximally entangled basis, I argued was equivalent to this procedure. And so by applying the inverses of these operations, I will have exactly A0 plus B1 in my laboratory. I might not know the value of A and B, but it's exactly the same state, just as good for whatever purpose I have in mind as if I had carried the state with me.
Now, nobody asked him how to make a C-naught cake. That's an empty question.
All right, and so, right, so there's now a law against C-naught questions. Okay, so what was the proposal of Horowitz and Maldacena in 2003? Well, they suggested that this is a nice way of thinking about how information gets out of black holes. So here is a causal structure or Penrose diagram for a black hole which eventually evaporates completely. This is the space-like singularity. This is the horizon. And some matter falls into the black hole. That's how the black hole formed. So how does the quantum information that was encoded in that matter get returned to the region outside the horizon? So what they said is, well, we can think of what's happening at the singularity as a projection onto a maximally entangled basis. We can imagine, or we can describe the Unruh vacuum, the state that looks like the vacuum to a freely falling observer who crosses the horizon, as just this state phi in some suitable basis, so a maximally entangled state. And what happens at the singularity is that the system, which I'll call N, the infalling Hawking radiation that's falling towards the horizon, and the outgoing radiation that's outside the horizon and propagates to infinity, that the infalling matter system and the Hilbert space of the infalling radiation get projected onto a maximally entangled state. There's a boundary condition at the singularity. The only state that's allowed to occur there is a particular maximally entangled state where S is some unitary operator acting on half of the state, which we'll be able to interpret as the black hole S matrix. So in this case, we weren't able to complete the teleportation until my friend called me up and told me what the outcome of this Bell measurement was, which of the four possible states had been found in her measurement. But what Horowitz and Maldacena suggested is that we can have a boundary condition which will admit only a particular maximally entangled state at the singularity. Only one outcome, if you like, of the entangled measurement is allowed. And therefore, there's no need for any classical communication from inside the black hole to the outside in order to ensure that the state coming out is related to the state that fell in by some unitary transformation. That this, again, is up to normalization, just the same thing as a process in which the infalling matter underwent some unitary transformation to become the outgoing Hawking radiation. Okay? So that's kind of a crazy thing to do, to say that only a particular state can be selected. But what do you think is supposed to happen at the singularity? Okay. They said, well, in other situations, quantum cosmology, for example, we're sometimes willing to entertain the possibility that we need some boundary condition on a space-like singularity to define unambiguously what quantum mechanics predicts. What should we do with future space-like singularities? They said, why not put a boundary condition there as well? And it has the nice feature that we can describe unitary quantum mechanics relating the infalling matter to the outgoing radiation as long as we really do project onto a maximally entangled state. The 1 over d is just a normalization factor. Normally, that's because this particular outcome would occur only with an incredibly small probability, 1 over d squared. But we're assuming that none of the other outcomes are allowed in this case.
So this is like Alice's measurement, except she could get any outcome.
She could get any outcome, and in
then-
fact,
and then
all of the 4 outcomes, if she were measuring in this situation, each one of those outcomes would occur equiprobably. So each would occur with probability 1/4. And that would be the same thing here if this were a measurement which projected onto any one of the elements of a basis of maximally entangled states. Our hypothesis is, though, that only one state is allowed to occur in that measurement.
So there can't be like an Alice who sits. The idea is not that there's an Alice who sits at the singularity, and whatever state that she finds.
No. There's just one state that's allowed.
Yeah.
But the probability of successfully
Yes.
obtaining that outcome doesn't depend on what the infalling state is, and that's why it's compatible with unitarity and no loss of information.
So a related question, this 1/d looks fairly innocuous, but really it's, well, the number of internal states of the black
It's a
hole,
big
so it's
number.
related to the energy that went in, so therefore related to the stress tensor and pretty non-local. Right?
Yes, and in fact, that's a good observation as far as, what is this unitary supposed to look like? Well, what we think is that black holes are great scramblers of information. So we threw in 1 million Steve Giddings, and what came out was almost unrecognizable because it was subjected to a very complex unitary transformation. And that all has to be encoded in this boundary condition in this scenario. Okay. So, why is this a nice picture? Well, I've already said it's nice to at least have an answer to the question, what happens to stuff that reaches the singularity? That's an answer. You may or may not like it. It also gives us sort of a concrete way of thinking about black hole complementarity. Normally, we find it rather disturbing if we consider the history of an evaporating black hole, that I can draw a nice slice through the space-time which crosses most of the outgoing Hawking radiation and also the collapsing body behind the horizon. Why do we find that disturbing? Because the same quantum state, some arbitrary unknown quantum state, appears at 2 places at the same time. That means the state has been cloned. Cloning of arbitrary quantum states is not compatible with the linearity of quantum mechanics. But in this picture, we can relax the rules. If we're considering post-selected quantum mechanics, where it's guaranteed that we're only going to consider one possible outcome of this entangled measurement, cloning is actually allowed. These really are 2 copies of the same state. They're related by some unitary change of basis associated with the black hole S matrix encoded at the final state boundary condition. But really, it's not so shocking that we have 2 copies of the state, because if you think about it in terms of the information flow through this diagram, it's as though we're looking at the same state but at 2 different times rather than at 2 different places at the same time. And so it's really the same state up to some unitary rotation. Now, the other nice thing about this picture is we can think about the situation that Ants discussed. Now let's suppose we have an old black hole. Okay? Old means that it has already radiated away more than half of its entropy. And for an old black hole, the radiation that's being emitted now is expected to be almost maximally entangled with radiation that was emitted earlier. And the problem that Ants emphasized is that that is impossible to reconcile with our expectation that the radiation being emitted now is also maximally entangled with modes behind the horizon, as we expect if the horizon is smooth and freely falling observers crossing the horizon see something that looks like the vacuum. So let me consider one particular state of the infalling matter and ask what the radiation coming out of an old black hole looks like in this post-selected scenario. So I'm going to call system B the radiation that just came out a short time ago. This is now supposed to represent where the horizon is. So these are two unrest states which are maximally entangled. System R is some subsystem of the radiation that was emitted a long time ago, which is expected to be highly entangled with system B. The unrest partner of system B, I'll call system A, and R also has an unrest partner, system H. So in this picture, now we're to imagine that we pick some particular state of the infalling matter, which means that the final state boundary condition is picking out some particular state of the infalling radiation. And what I'd like to understand is how it's possible for this state to be maximally entangled. That means the horizon is smooth. And also for B to be maximally entangled with R. Normally, we couldn't have it both ways. Entanglement is monogamous, and B can't be maximally entangled with two different systems. But subject to post-selection, it can be. And so in this picture, it's really equivalent as far as the information flow is concerned to this one, in which a maximally entangled state of BR is prepared. And we can later on verify that entanglement by doing some appropriate entangled measurement like this one. If I do the measurement in the right basis, I'll get some particular outcome with probability 1 verifying the entanglement. So in ordinary quantum mechanics, entanglement is monogamous. But in post-selected quantum mechanics, that monogamy can be relaxed. And that's just what we need to address the problem that Amps pointed out. Now, this picture isn't guaranteed to work. There are ways for it to fail. And what can be particularly problematic are interactions behind the horizon between the infalling matter and the infalling radiation. So if such interactions occur, described by some unitary transformation, the picture can be modified this way. This is the infalling matter, the outgoing radiation. The infalling radiation, here's where the final state is projected out. But if this unitary is some entangling unitary acting on the matter and in systems, then in effect we might not be projecting the tensor product of M and the in-Hilbert space to a maximally entangled state. And that will mean that we won't have perfect unitarity. There will be some loss of information. So we have to have some restriction on what...
Sorry, can I get this point clear? So when you say non-unitary in this case,
Yeah.
so normally when we think of loss of information, you think of a pure state evolving to a mixed state.
Mm-hmm.
In this case, it seems to me it's a pure state evolving to another pure state by a non-unitary transformation that makes it no longer necessarily normalized. Is that correct?
Well, yes. So
it's still linear. It doesn't in the wave function psi.
right.
It's no longer a probability.
But it's not. No, it's just not invertible. So, for example, suppose, to give an extreme case, that this is a unitary which maps the maximally entangled basis to a product basis. And so what we're doing could be described this way. So the infalling matter is subject to post-selection, and the in and out states are also projected onto some particular final state, but now it's a product state. So it's possible if M is orthogonal to the state that's projected for that to be something that occurs with zero probability. But at any rate, just some particular state is accepted. but that incoming state is completely uncorrelated with the outgoing state. So that's what I meant by loss of information. And for any situation in which we project onto a state of M tensor n, which is not maximally entangled, there will be loss of information in that sense. We won't be able to reconstruct the incoming state from the outgoing state.
Yeah, that's a very non-generic final boundary condition.
Yeah, that's right.
It's a sort of typical state.
Well, I would just chose it for
Right.
purposes of
And
illustration.
essentially, your matrix going from the into the out has 0 eigenvalues in it.
Well, as
If
long as
it's
you brought it up.
small, then you can still reconstruct the in state from the out state.
Up to some error.
No, I think perfectly.
Oh, I'm sorry.
It's just by a transformation that is not a unitary transformation.
Oh, well, okay. You're right. I'm interested in whether it's possible to decode the information with the unitary. Right.
Sure.
Right.
It's just that it sort of seems like a different type of non-unitarity from the, say, you get in the Hawking calculation. It sends pure states to pure states, but changes the normalization.
That means some probabilities are different. Probabilities don't have to one.
Yeah, which is a serious issue. And you can always force them to add to 1 by hand, but then you have, retro-causality.
As long as you brought up the question of typicality, let me say something about that. I think I didn't say, I wrote a paper about this with Seth Lloyd, and everything that I've said pretty much is in that paper, which we wrote last year, including what I'm about to say, which is, and actually Seth pointed this out in a paper 10 years ago, we could ask what happens if we don't choose any special boundary condition, we just project onto some randomly chosen, uniform with respect to Haar measure, state of the M tensor in Hilbert space. And what happens is kind of interesting. Actually, let me describe it this way. Let's suppose we divide the matter into 2 subsystems. So what I'm calling M1 are the states which can collapse rapidly to form a black hole in the way we usually picture black holes forming, as opposed to the typical states of black holes which we can only make over a much longer time period comparable to the evaporation time, carefully focusing radiation in. So these rapid collapse states are very sparse in the full Hilbert space. The dimension of the Hilbert space is something like e to the minus order the black hole mass to the 3/2 instead of mass squared. Okay? And so now, let's suppose I consider just fixing the state of M2, because I'm only interested in rapid collapse. And this is the system M1. And then describing projecting onto a Haar random state is equivalent to saying I do some Haar random unitary and then project onto a fixed state. For the purpose of understanding what happens, I can imagine maximally entangling the M1 Hilbert space with a reference system of the same dimension, N1. So I have a maximally entangled state of M1 in the reference system. And if in this process the system N1 winds up being maximally entangled with the outgoing Hilbert space, that means that M1 can be decoded. Okay, it means that I can extract the maximally entangled state of N1 and out by performing some unitary decoding just on the out Hilbert space. But I'd like to imagine now that the out Hilbert space is much larger than the M1 Hilbert space because we're only looking at the states that can form from rapid collapse. Actually, another way of saying what I've done here is I've projected onto some Haar random state in the Hilbert space of the reference system and the out Hilbert space. And something that you probably know is that if you consider a random state of a joint Hilbert space of two subsystems where one subsystem is much smaller than the other, that will be very close with high probability to a maximally entangled state of N1 with some subsystem of the out Hilbert space. And you can turn that into a more quantitative statement that if we average over these unitaries, which is the same thing as averaging over to the averaging over the Haar random state in the boundary condition, and I look at the marginal state of the reference system when I apply that unitary and ask how close it is to the maximally entangled state in the one norm, which is the right one, because states that are close in the one norm can't be distinguished by any measurement, then this is less than the square root of the ratio of the dimension of the M1 Hilbert space, which is the same thing as the dimension of N1, divided by the dimension of the out Hilbert space. And that's incredibly small if I'm considering some small subsystem of all possible matter states. It goes like e to the minus the black hole entropy over 2 from this denominator, but then with some correction, which is order black hole mass to the 3 halves, which is subleading. And so if we just choose some generic boundary condition, then the conclusion is that we can successfully do the decoding and recover all the information about what fell in with high probability of success, aside from some incredibly tiny error, which is exponentially small in the black hole entropy. And that's kind of encouraging because this is a rather naive semi-classical picture, and we wouldn't really have a right to expect it to work so well that we would get, get the right answer, including corrections which are as small as e to the minus black hole entropy, which can include very rare quantum effects. So it looks like maybe it's not such an unreasonable thing to say that the boundary condition will be such that we can successfully project onto a maximally entangled state and get all the information out without any loss of information, even if we don't have to carefully tune the boundary condition.
This is get out all the information that comes in rapid collapse.
Yeah, at least in rapid collapse. And in the case where there's not rapid collapse, I would have to do a more complicated analysis because I'd have to worry about how the stuff coming in collided with the stuff going out and so on. But at least this is a check that things aren't crazy. Right. So, and something else we discussed in the paper. Well, I think I'll skip that because I'm running behind. So I want to talk about measurements. And the point is that I'm not just interested in generic things that can happen. The idea of AMPS was we should look at situations that really test the theory, that back it up against the wall where it can run into trouble. And so we should try to do that. The types of measurements that AMPS considered are not generic phenomena. We have to do something very careful. We have to decode the Hawking radiation in just the right way to check its entanglement with the recently emitted Hawking radiation, and then we have to compare that with some other particular measurement. So it's not enough just to talk about how things work great under generic situations. We're entitled to ask what happens in more special situations. And so now I want to think about measurements that are performed by observers who fall into the black hole. Perhaps these are measurements that involve entangling observables of the outside system and the inside system. That observer can interact with the outside first, cross the horizon, and then interact with the inside. Of course, that observer is then going to be stuck inside the black hole, and if we stay outside, we might say, who cares? Because that observer is going to be destroyed at the singularity. But not really, right? Nothing really gets destroyed. We think that the overall story is unitary, then anything that happened to that observer behind the horizon winds up encoded in the Hawking radiation that's been emitted by the time the black hole has completely evaporated. And if we're willing to perform some superhuman feat of archaeology, we could decode that record by doing a complicated decoding map on the outgoing Hawking radiation, and we have all the time we need to do it. I don't mind if we don't finish decoding it until after the whole black hole is gone. The information is still there in the Hawking radiation somewhere, and in principle we can get it out. So we can ask about what happened to the meter that the observer carried into the black hole, coming out of the radiation in some highly scrambled form.
Does that argument really work? Because what you've discussed so far is that the incoming information comes out unitarily with the right boundary condition to the stuff outside. Now you're saying that stuff inside the black hole is unitarily related to stuff that comes out.
Well, I think the overall story has got to be unitary. So I'm entitled to ask about the asymptotic incoming state and asymptotic outcoming state.
So
the asymptotic incoming state includes the observer who carried a meter and crossed the horizon and eventually came out in the Hawking radiation. So the unitarity that I'm demanding is that overall unitarity, relating all the stuff that fell in, even if some fell in earlier and more fell in later on, to all the outgoing Hawking radiation.
Yeah, but does that necessarily mean you have a unitary interpretation of every single step?
Well, that's what I want to discuss, right. So, for example, we can imagine, I might need this, so I think I'll keep it. So I'm interested in particular in measurements that are performed on the infalling Hawking radiation behind the horizon, because that's what comes up in the AMP situation. And so let's think of a picture like this, where one of these systems, one of the lines represents the infalling matter, and the other represents an ancilla, which we threw in later on. And behind the horizon, that ancilla interacted with the matter. Then the ancilla and the matter arrived at the singularity, and they got projected onto some maximally entangled state. So a situation we can consider, not the most general one, but one of interest if we want to talk about a measurement in this setting, is the one in which the ancilla and the matter are teleported out of the black hole independently. Each one is matched up with a subsystem of the infalling radiation, two separate subsystems. And so now we're interested in the relation between the incoming state of the matter and the ancilla and the outgoing state. The ancilla and the matter are all scrambled up, so we'll have to work hard to get that state out, but in principle we can get it out and do anything with the ancilla we want to make inferences about what happened when the measurement was done. Now, this is not at all guaranteed to be unitary. To draw it in more detail, we're considering a situation that looks like this, where this is the ancilla. So this line for the ancilla, I can just imagine just straightening it out, because it's equivalent to this. So the ancilla, when it's still, so to speak, moving forward in time, interacts with the matter system when it's going backward in time, in other words, with the infalling radiation, which it will be paired with at the final state boundary condition. So now here's the ancilla. Actually, I guess I want this to be ancilla. Here's the outgoing radiation. Here's the end state. So this is an interaction between the ancilla and the infalling radiation. And even though U is unitary, this might not be unitary. In fact, it's equivalent to this situation in which I have both the matter and the ancilla propagating forward in time, this becoming the out state and this the ancilla. But where the unitary is, PT stands for partial transpose. It means I've interchanged the, the bra and the ket for the matter and out system, but not for the ancilla system. So in order to reconcile the time ordering for the ancilla and the meter, I had to do this partial transpose. And in general, the partial transpose of a unitary isn't going to be a unitary. Okay? But that's actually equivalent in this setting to saying, as I did earlier, one of these is the ancilla and the other is the matter, that we want to make sure that the overall state gets projected onto a maximum entangled state because that's necessary for unitarity. And that's actually the same thing in this setting as the condition that the partial transpose of the unitary U is also unitary. So if we're going to insist on overall unitarity, that means operations of this type performed between the ancilla and the infalling radiation have to be one such that the partial transpose is unitary. But that includes a lot of interesting transformations, and in particular it includes the type of unitary that we would do if we wanted to consider a conventional von Neumann measurement, in which we would say that we have some system, let's say the matter system M, that we want to measure, and some corresponding meter. And for a complete set of orthogonal projectors of pi ma, when pi ma acts on the matter state, there will be a corresponding shift by A in the meter. So this is a unitary transformation that will entangle the meter with the particular decomposition of the Hilbert space into some basis defined by this orthogonal projection. And if we do the partial transpose, that just means taking the transpose of this projection, but that's just another orthogonal projection. It's just its complex conjugate. So it's still unitary, and just another measurement when we take the partial transpose. Okay? So I want to be liberal-minded when it comes to what the observers who fall into the black hole are entitled to do. This is a measurement that normally you and I like to do. We entangle a system with the meter, and let's allow our observers inside to do that too. It's consistent with unitarity. It has the property that we needed, that the partial transpose is also unitary. Okay? But even if we do that, we can still get into sticky situations if we consider as we may want to in the setting considered by amps, entangling measurements across the horizon. An observer who interacts first with the system outside, then crosses the event horizon and interacts with the inside system. So we can get a picture like this, where the ancilla interacts first with the radiation escaping from the black hole, then falls into the black hole and interacts with the infalling Hawking radiation. what's strange about this circuit is that it's chronology violating in the sense that there isn't any globally defined forward direction of time shared by the ancilla and the matter. From the ancilla's point of view, it interacts twice with the matter. The first interaction is V1 and the second is V2. From the matter, going to the outsystem point of view, it interacts twice with the ancilla. The first interaction is the partial transpose of V2, and the second is V1. So the order in which the two interactions occurred seem different from the ancilla's point of view than the matter's point of view. And that's what I'll call chronology violating, meaning we don't have a globally defined way of defining for the information flow a forward time direction. Okay. Now, that really means that potentially causality violating things can occur. But in the case of a young black hole, it's not so bad. We might have a situation like this. Where the ancilla interacts with the infalling matter behind the horizon, and then the ancilla later is radiated in the Hawking radiation. And so here, Hawking radiation pulled away from the horizon. And the state of that Hawking radiation is going to be modified by an interaction that occurs later from the point of view of the outside space-time, an interaction with an ancilla that across the horizon. But that's actually not much different from what we normally expect in the case of a young black hole. Because really what we're saying is that when this radiation first comes out, it's nearly maximally mixed. It's essentially featureless. Much later, the ancilla is going to come out in the Hawking radiation. And when it is radiated, it will wind up being entangled with this radiation that was emitted earlier. Well, that's just the type of phenomenon that we expect. If we have an evaporating black hole and we throw in some additional stuff, then that stuff will get rapidly scrambled with the remaining internal degrees of freedom of the black hole. And when radiation comes out, it can be entangled with the radiation that was emitted earlier. And that's really all that I'm describing here. But the more troubling things that can happen are in the amps scenario for an old black hole. As in the picture I drew earlier. Now we have an ancilla, which falls into the black hole and will eventually come out in the Hawking radiation. It interacts with the infalling radiation behind the horizon. And so if we hadn't thrown in the ancilla, when system B started to pull away from the black hole, it will be maximally entangled with system R, and in principle, we could do a decoding operation to check that. Later on, we decided to throw in the ancilla. And now it will turn out that system B is no longer in a pure state with system R. What happens instead is that B is purified by the composite system consisting of R and the ancilla. Okay? And we won't be able to check that B is maximally entangled with something until that ancilla has also been radiated out. So it winds up, system B, which we thought was going to be entangled with this previously emitted radiation, winds up being entangled with previously emitted radiation and also later radiation because we threw in the ancilla. So what I want to do is, I guess, I've probably used up my hour. Okay. So I want to say a little bit about what happens if we actually do the measurements to try to verify the entanglement, which is what AMPS told us to do, to check that B and R are entangled and to check that A and B are entangled. Okay? In this type of scenario. So let me first tell you the answer, and then if I have time, I'll tell you how you calculate it. So now, same picture again. HABR. And now I'm going to consider two observers. Actually, I don't have to consider an observer who crosses the horizon. It'll actually be enough. Well, sorry, one of them is going to cross the horizon. But I don't have to have the observer who checks the BR entanglement carry that record into the black hole and compare with the result of a measurement performed in the black hole. It's enough to have two observers. I'll call them Brenda because she measures BR, and Abby because she measures AB. Okay? And they each have a meter, and they both do sequential measurements. So this is Brenda's, and this is Abby's. And Brenda, of course, she has to do a fast decoding of the Hawking radiation. So let's not worry about that and suppose that somehow she manages to do that. And so she is able to perform an entangling operation between her meter, which she has in her possession, and system R, which she's managed to decode. And then after doing so, the order doesn't really matter, but in this case, after doing so, she performs some other entangling operation on her meter and system B. And now, in principle, she can read out, by performing a measurement on her meter, the state of BR in some entangled basis, like I was describing over here. Okay? And so Abby's going to do the same thing. For Abby, the order does, in principle, matter because of the causal structure. She's going to do the measurement sequentially as well, but she has to interact with system B first outside the horizon, then with system A after she enters the black hole. So these are her interactions. First of all, an entangling interaction between system B and Abby's meter, and then between system A and Abby's meter. Okay? Now, if the measurements had been done in the other order, if Abby had done her Bell measurement on system AB before Brenda had done her measurement, then everything would have worked fine. She would have successfully projected onto the expected state this maximally entangled unrest state. And Brenda's measurement would have worked fine too. In order to turn this situation into the one in which the measurements are performed in that order, first Abby and then Brenda, I have to do one thing. I have to commute this entangling operation between Brenda and system B with this entangling operation between Abby and system B. Okay, but they don't actually commute. So I can move this one past this one, but when I do so, I induce an entangling interaction between Abby and Brenda. So what does it mean? It means that actually the outcome of both measurements is encoded in this pair of systems, Abby's meter and Brenda's meter, but the measurement has become twisted. If I want to read out the result of the measurement BR, I can no longer do so just by reading out Brenda's system. I have to bring Abby's meter and Brenda's meter together and perform some entangled readout of the two. Okay? In fact, what actually happens is that if Brenda were not to do that and just perform a measurement on her meter alone, she would get a random outcome. And so it would seem to her that the system BR had a probability 1 over d squared of being in the right entangled state, and Abby would find the same thing. But if we're willing to wait until Abby's record gets radiated out of the black hole, we can undo this entangling operation between Brenda's and Abby's meter and read out the result and get the right answer. So a possible interpretation is that it's not that the entanglement is being broken by performing the measurements in this order, first Brenda and then Abby, but the measurement is getting twisted. Okay? And in fact, one way of checking that is we can imagine repeated measurements. I'll come back to that in a minute. But there's still something non-local occurring outside the black hole. Because if we just look at it from Brenda's point of view, she performs what she thinks is the right entangled measurement on system BR. And if she were to read out her apparatus right away, then if Abby doesn't later on jump into the black hole and do her measurement, then she'd get the right answer with probability 1. If Abby is going to later on jump in and do her entangled measurement, then she'll get the right answer only with probability 1 over d squared. So that's what I mean by causality violation or non-locality in this setting. But what's happening that's non-local is an interaction between the two meters, okay, which we can undo once Abby's meter gets radiated out in the Hawking radiation. So if you'll give me maybe 5 minutes, I'll explain in more detail how that worked, or is that okay? Because that's where I can come back and use this, which will save me a little time. So let's suppose I think of each one of these systems as being qubits. Conceptually, it wouldn't matter really if they were higher dimensional systems. So this is in fact exactly what Abby and Brenda are doing to do their Bell measurements. And actually, to illustrate the point I want to make, it's not really necessary for them both to do the complete Bell measurement. It's enough if one of them measures Z tensor Z on, say, B and R, and the other measures X tensor X on A and B. So now those are non-commuting measurements, which is why we're having a problem. Okay? And so if Brenda measures first, we get a picture like this. So Brenda is trying to measure Z tensor Z. Abby is trying to measure X tensor X. Here's A, B, and R. And so in the end, we're supposed to measure this ancilla in the X basis and this one in the Z basis. So what Brenda does is first she performs a C0 on system R and her meter, and then on system B and her meter. And that would be a measurement of Z tensor Z. And then Abby is trying to measure X tensor X, and she has to do it in the right order, but she just does a C0 from her meter to system B first. This H looks like an A, but it's actually an H. And then she does the C0 from her meter to system A. Okay? Now, if Abby measured first, then this C0 would be performed first, and we'd get exactly the expected answer. Okay? So all we have to do to transform this diagram to the one in which they're guaranteed to get the right answer, they do the measurements in the other order, Abby first and Brenda first, we have to commute this C0 through this one. Okay? But they don't commute. But there's a simple identity which says, okay, if I have system plus B minus the two ancillas in system B, and here I'm doing the C0s in this order. I want to change the order, so I do this one first. But these are two ways to describe the same operation if I add this one additional C0. Now, if you look at how these act on a basis, So in this case, we're adding the value of this register to this one and adding the value of this register to this one. And this does the same thing. It looks like it does it wrong because it added the sum of this register and this register to this one, but then we undid that with the last C naught. Okay? So I can commute the two C naughts. Now I get the measurements in which the right answers occur with probability 1. But all I've done is I've added one more C naught between the two meters, X and Z, like that. And so if Abby and Brenda want to decode their results, when the ancillas, this should have been 0, I guess, when the ancillas get together, they perform one C naught, which undoes that extra C naught, and then measure this in the X basis and this in the Z basis. So like I said, this really is from the point of view of the bulk space-time outside the horizon, something non-local, because the Z winds up being, or rather Brenda's meter winds up being entangled with Abby's if Abby is going to throw hers in later on. But that affects the marginal state of Brenda's meter right away. If Abby is going to throw it in later on, then the measurement has to give a random outcome, unless this non-local effect is undone later on by applying the C naught to properly decode the measurement. So what are we supposed to conclude from all this? We have a setting in which we can talk about horizon straddling measurements. That's nice. We have some understanding of how to think about the amps measurement. But we have these strange non-local effects occurring outside the black hole. You could say this is evidence that the right attitude was what actually Seth and I suggested in our original paper, which is there are certain things we just shouldn't allow inside observers to do because they create these non-local effects which can be detected outside the black hole. And that doesn't really seem fair to me. I mean, it seems to me that if Abby wants to measure, we should let her measure. And there's some operational meaning to that and to the outcome she obtained because her meter will eventually be blasted out of the black hole in Hawking radiation and can be decoded later on. You could say it's evidence that post-selection just isn't the right approach for trying to understand the amps puzzle, that it leads us to these perhaps insuperable difficulties. You could say it's evidence that maybe it really is firewalls and all this standing on our head doesn't allow us to evade that conclusion. There's an interesting question that, from a quantum information point of view, is an interesting question to ask, which is, if this picture is the right one and we can do these measurements which can have a causal effect, what is the computational complexity of that model? How hard is it to simulate it? Simulating it by brute force doesn't really work. We can do all these unitary, in general it doesn't, we can do all these unitary interactions, and then we want to simulate the entangled measurement, but the outcome that we want occurs only with exponentially small probability, so we'd have to do that simulation an exponential number of times. On the other hand, in the type of process I've described here, the circuit turns out to be equivalent to one which can still be easily simulated. Maybe we have some polynomial in the number of black hole qubits, number of gates in the space-time process, as well as a post-selected boundary condition, but we can still simulate that with some polynomial number of gates. So we haven't gotten any additional computational power by including post-selection. That's what I thought the answer was originally when I thought maybe we should have the attitude that these strange non-local things don't happen outside the black hole. Now it seems less obvious. So I don't claim to know the answers. I don't know whether there are firewalls. But I think, all this we're finding out, or it's being driven home to us in the last couple of years, that although we think we have, in the case of ADS-CFT, some nice unitary picture of the formation and evaporation of a black hole, trying to extract what that is telling us about the bulk spacetime, particularly behind the horizon, has turned out to be surprisingly elusive. And it may be ultimately that what I'm talking about here fits into that picture, really is compatible with having some reasonable local unitary boundary theory. But I think part of what I'm trying to emphasize is that we should be willing to kind of think broadly about what the possibilities are for understanding physics in bulk spacetime to resolve these puzzles. Okay, thanks. Sorry for going late.
So one quick comment is that we'll be going to dinner, I believe, around 5:30. So if you're interested, we will be leaving from right outside here at 5:30. So talk to me about that. But since we went over a little, maybe we can just have 1 or 2 questions for John, and then hold the rest for afterwards.
Mark.
So this, let's say I believe in post-selection, believe everything, and there's going to be this non-local effect. Can you describe this non-local effect in the direst terms possible?
Make it sound
How bad is it? Yeah. What's the worst, the most horrible thing you can do? Because it doesn't sound that bad to me.
Yeah. I don't know. I don't have a horrible scenario to report, but I haven't thought about it enough with the proper frame of mind.
I think you have to go through with a horror movie frame of mind.
Maybe like in Minority Report where those little balls come down saying who's going to kill somebody in the future.
Yeah, maybe. I kind of fell asleep with that. It wasn't dire enough.
Steve.
You were saying that this is not just non-local, but also a causal?
Yeah.
theorem?
Yeah,
Okay.
I did say
So it's
that.
equal- all right.
Well, I told you what I meant by that.
Yeah.
That if I want to compare two situations, in one of which Brenda does her measurement and Abby decides to go home and not risk going inside the black hole, and the other situation in which Abby really will, after Brenda does her measurement, go into the black hole and do her measurement, that Brenda, what this scenario is predicting is that if Brenda does the readout of her meter immediately after her meter interacts with systems B and R, she will get a different outcome because Abby is going to jump in later than she would if Abby does not jump in.
And can she know in advance which outcome is which? This is what confuses me.
Oh,
I mean, the dial is going to point to something. And does that dial immediately tell Brenda whether or not Abby jumped in?
It does.
Yeah, so it is
if
one-
you have
Yeah.
the theory of the universe.
Right,
yes.
right.
yeah, I mean,
It's like one of these little balls
Yeah,
that comes
yeah,
through.
it tells her whether Abby will jump.
yeah, it tells her. I mean, I'm taking a lot of things for granted,
Yeah,
right?
sure.
That Brenda is able to isolate system R that's supposed to be entangled with system A. But if she has done that successfully, there's a particular outcome of her measurement that should occur with probability 1, but will actually occur with probability 1 over d squared. Well, in this case, 1 over d, 1/2, in fact, if she's just doing one measurement of a qubit. And so, just to be sure, she could repeat the measurement several times, and every time she repeats it, the same thing happens. If she has, what I mean is, if she measures 10 times, she will get a random outcome every time if Abby is going to jump in later.
So this seems very good, because these are measurements that can be made in the dual CFT, I think. They're external measurements.
Yeah.
I mean,
They are if we understand both the boundary map in the obvious way. As long as there's
Wait,
no additional.
do we need to understand it?
Yeah,
do we need,
because
do we only need, what?
Brenda has to do her measurement of B early enough that Abby can then measure B afterwards and still jump in. And
Right. Yeah, that's a kind of right. But basically, B can reach the boundary in time order 1, and Abby has a log time after that to jump in. So,
Log time after.
a scrambling time after that to jump in at BA. We can suppose the time for B to reach the boundary is much less than parametrically can be made smaller than the scrambling time.
Sorry, doesn't Abby have to catch one of the infalling?
Yes,
photons?
but she has a scrambling time to do that.
No, she has an infall time to do
Oh, you say she cannot.
that.
So
Yeah.
she
So
doesn't.
it's not so bad, right? It's not like you have to probe things that are very close to the horizon, but you have. But if there's some if there were, to make this consistent with ADS-CFT, I think what you need is some additional non-locality of the dynamics in the fault, which has not yet been brought to the fore.
Okay, so
which is in fact also acausal, because it depends on, for example, whether Abby jumps into the ADS space at some later time.
Yeah. Okay, but it's not clear that it can't. It's not actually something that the problem that lives in the CFT.
No, it involves the bulk pattern.
Okay.
So it's not a sharp contradiction with ADS-CFT, but it does require, to make it consistent, requires additional non-localities and acausalities in the dynamics of the bulk that have not yet been turned into the bulk. So it requires the propagation of photons from near the black hole to the boundary depend on whether Abby will.
So why isn't this argument that sort of the inside a scrambling time to recapture? I mean, that requires like someone inside to.
Which argument?
In sort of some of the original thought experiments where an observer measured the Hawking radiation and the photon inside, I thought they had a scrambling time.
I think that was overkill. I think
to catch up with the inside.
I think that you found. What was that? I forgot the thought experiment.
Well, just the very basic one where you measure the outgoing radiation, then you jump in and see the clone inside. And the statement was that I mean, this was one way the scrambling time was originally understood, that as long as the outside copy came out with a scrambling time later, you couldn't see both the outside and the inside clone. But if it was less than the scrambling time, you could. And this had to do with this had to do with
It's just the exponential redshift.
the exponential redshift.
Mm-hmm.
Right. Now maybe that required an extra observer inside to kind of catch the inside photon and direct.
Well, there was
it out.
communication on the inside.
Right. It required it. Yeah.
I'm sorry, it depends on how close to the black hole horizon you allow Brenda to probe this entanglement. Yes, if you allow her to probe it a plane distance outside the horizon, then you get a scrambling time.
I'm sorry. You say I've already lost. I'm sorry. Your point is I've already lost the scrambling time getting from the horizon to.
Yes, that's the scrambling
time.
So if you want to view it as something that happens at infinity, you have time.
No. Yeah. So.
Rather short.
Okay. So really. So good.
I'm not sure.
So if I understand quantum mechanics purely in the bulk, we have to.
Couldn't you use this also to produce closed time loops for information? It's basically the problem of sending signals.
Well, I thought about that some, and so people talk a lot about using post-selection to simulate closed timeline curves, and it's been studied what kinds of computational power that gives you and so on. But the powerful things that you can do, it's not obvious how to simulate, at least it's not obvious to me yet, how to simulate those in this type of scenario. So for example...
It looks like you can send a signal back depending on what Abby decides to do, whether or not a particular horse wins at the racetrack, she can either jump in or not, and you can send a signal back in the sense that Brenda knows the answer long before the event's going to happen. Right?
Mm-hmm.
So,
well, that's what I meant by causality bias.
Okay. So, but then, so that typically leads to inconsistencies, right?
Well, I'm playing by special rules, which are that the overall evolution is unitary. So that actually makes it, so a lot of things that people talk about for simulating closed time-like curves using post-selection involve non-unitary operations. But I want the overall operation to be unitary. Let's say that's our inviolable principle. Well, what I've tried to emphasize is that doesn't mean that you can't do these measurements inside the horizon. There's still a unitary circuit that relates the initial state to the final one. It just has these extra entangling interactions that we didn't expect. But that restricts a lot the types of signaling you can do.
All right, so why don't we table any further questions for afterwards, and thanks for having us.